Feynman's gravity scales. An analysis of observational precision, the massive Planck scales gap, and the mathematical boundaries of the Spin-2 quantum field approach. The beauty of Spin-2 field. A unified language. Instead of viewing gravity as a unique outlier that is strictly geometric, Feynman's approach models it identically to other quantum fields in nature. Electromagnetism relies on a spin-1 photon. The strong force on spin-1 gluons. Gravity relies on a spin-2 graviton. The authors love the beauty of Feynman's model of gravity for its conceptual symmetry. The tensor gauge field. Space remains a flat, intuitive container. We avoid spaghetti-like curved coordinates. Self-interaction of gravitons creates the illusion of spacetime curvature in the weak field. Energy generates gravity, and gravity is energy. This loop sums to Einstein's equations. The purist's backlash. The renormalization hurdle. In standard QED, infinities are cleanly absorbed into physical mass/charge. In the 1980s, physicists' math trick fails for spin-2 gravitons due to their infinite self-interactions. The pure math retreat. Because the theory required infinite counterterms to resolve, mathematical purists declared Feynman's model dead and retreated to highly abstract mathematical models like string theory. The inconsistencies were observed at high energy and small scale. Let us compare observational facts with the massive Planck scales gap and the mathematical boundaries of the Spin-2 quantum field approach. The scale of length. Exploring the frontier of physical measurements and subatomic records. Subatomic precision limits. The LIGO record. LIGO can detect distance perturbations as small as 10 to minus 19 meter. This is 10,000 times smaller than a proton diameter. It stands as the absolute microscopic measurement record of humanity. The LHC micromap. CERN's Large Hadron Collider probes matter structure down to 10 to minus 19 meter. Up to this extreme frontier, quarks and electrons behave as perfectly point-like structures with no measurable internal spatial layout. The Planck Desert. The absolute limit of coordinates. The Planck length boundary lies at 1.6 times 10 to minus 35 meter. The leap from our best measurement limit down to the Planck length is proportionally identical to traveling from the scale of a domestic cat up to the boundaries of the entire observable universe. The scale of energy. Natural and artificial energy densities versus the quantum gravity breakdown point. Comparing cosmic energy scales. LHC max proton collision. The Large Hadron Collider LHC at CERN produces a total collision energy of 14 tera-electron-volt. The LHC squeezes this amount of energy into a space billions of times smaller than a single proton, creating extreme temperatures and densities mimicking the Big Bang. Oh my God particle. It is the highest energy cosmic ray ever observed at 3.2 times 10 to 20 electron-volt. This single subatomic particle packed about 40 million times more energy than protons accelerated in the Large Hadron Collider. To reach this scale of energy, the particle was traveling at nearly the speed of light. The Planck energy in comparison. The absolute limit of energy. The Planck energy is a fundamental theoretical limit at 1.2 times 10 to 28 electron-volt. At this energy scale, the gravitational forces between particles become as strong as the quantum forces. To probe this energy level artificially, a particle accelerator would need to be the size of the Milky Way. Feynman's flawless domain. The safe haven. Across all accessible measurement domains, below 10 to 20 electron volts and above 10 to -19 meter, Feynman's quantum spin-2 gravity theory operates with absolute, flawless accuracy. The mathematical divergences are entirely suppressed, and the theory matches the predictions of classical general relativity to precision limits. The mathematical limit. The equations only spiral out of control when we mathematically compress gravitons down to the Planck limit. Comparing a standard household candle to the atomic bomb dropped on Hiroshima illustrates how far these mathematical problems are from reality. Completing the standard model of particle physics. The spin-2 graviton entry. When framed as an effective field theory, Feynman's spin-2 graviton completes the fundamental puzzle. It allows us to seamlessly integrate gravity alongside quarks, leptons, and bosons without worrying about the purely mathematical crises at the Planck limits.